Hey everyone, welcome back to my channel. In this episode, we will learn how to solve time-independent Schrödinger equation numerically by using shooting algorithm, and especially the Numerov integration technique will be used. We know this is our time-independent Schrödinger equation for harmonic oscillator in non-dimensional form or in scaled form. Here all the symbols have their usual meaning. Here psi is the dimensionless wave function, is the energy eigenvalues, x squared is the potential function, uh, and if you write this equation in terms of some k, here d2 psi dx2, that is equal to some minus k psi. If the first derivative is missing in any this sort of equation, then we can use the Numerov technique for integration, numerical integration. We know the numerical Numerov formula is something like that, that is psi n plus 1 is the wave function at a particular n plus 1th point, that is based on the wave function at psi n and psi n minus 1, and h is the step size in spatial grid, and k is defined as this e minus x square. Here in especially x square for harmonic oscillator, basically it is Vx n, and n minus 1 is the previous grid point and n plus 1 is the next grid point, and you are solving n plus 1th point on the based on the knowledge of n minus 1 and n plus 1. I will discuss the new how to get the Numerov formula in different episode, but here we assume the Numerov formula here. And if we solve this in a scaled form, the energy rescaled energy values will be 1, 3, 5, etc. Actually it is half, 1.5 and etc. For analytical, from the knowledge of analytical calculation that we know, and I am not discussing detailed here. And for 1D box, this will be something like that, and reduced energy eigenvalues are basically whatever may be the energy value and multiplied by 2, which is n square pi square by 4. So ground state energy is pi square by 4 and fast excited energy is pi square, and you can do that, and this will be matched with our numerical results. And here we already have said, here we use the shooting algorithm. And shooting, what is shooting algorithm, I have discussed in earlier video, you can check that video. And but I am here discussing little bit. Shooting method is a numerical technique used to solve boundary value problem like time independent Schrodinger equation. The main idea is to guess the value of unknown initial condition, typically the energy of in quantum mechanics in this case, and then integrate the differential equation from one boundary to other. The goal is to adjust the guess energy level until the solution satisfied at the other boundary, boundary or both boundary, whatever the methods. And that is, first you have to define the potential and the boundaries, define the potential Vx, and define the boundary wave function, boundary condition for wave function psi x. Basically we whatever may be the potential, we always put a dead wall at both end of the boundary. That is the boundary condition. At the dead wall, the wave function must vanish. That is the main artifact in this calculation. First you have to guess energy value. The guess does not need to be very accurate, but it should be range where the solution is expected. What is numerical integration? There are different numerical integration technique can be used, ODINT in SciP, or Numerov method, or Euler method, or RK2, whatever. But here we use the Numerov method. First you have to integrate TISE from one boundary, say x equals to xl, to other boundary x equals to xr using numerical methods like Numerov method, and start with initial value psi at L is 0 and a small positive value, that is psi 1, that is which is psi 1 later in the program, psi xl or small step plus h, that is small value, say 0.001. And with this starting condition we go to the another point by numerical integration, that is propagator, from you are going from one point to another point using the integration technique, and you have to check what will be the value of psi r at the other boundary. If it is 0 or very close to 0, then the current energy level is the correct eigenvalue. If not, then you have to adjust energy and repeat the integration again iteratively. You have to do that, and from there at a particular energy level, when the psi at the other boundary, at the right side of the boundary is 0, then you have the actual energy eigenvalue, and you have to iterate and converge, and you can adjust the energy using any method like root finding methods, that is bisection or Newton-Raphson, which satisfies the boundary condition. That means other boundary, the psi r must vanish, and the energy satisfies the boundary condition at both ends is the desired eigenvalue, and corresponding eigenfunction, corresponding psi x is the eigenfunction. How to do using Python? I am just discussing this. First you have to import some necessary libraries, np for numpy first array, matplotlib.pyplot as plt for plotting, and scipy.optimize bisect for root finding. And then we have to define a domain for our wave function, say L equals to 5, and to capture the wave function properly, and the domain is symmetric from minus L to plus L, and you discretize the domain from say for 501 points. So x comma h np dot linspace xl to xr, that is minus L to plus L, and return step true, that means the step size between 2 points is h, and floating, it is a floating point object, and here you get the x array over which you integrate the whole thing. Next we define the potential energy function for harmonic oscillator, that is x square, def f as function, vx which will return x square, and then we have to integrate integrator, use some function which is Numerov E, integrates the equation for a given energy E and returns the wave function psi x. So Numerov def Numerov which with value E, there is a wave function psi np dot zeros which having the dimension n, and what is n, that is 501, and type is float, data type is float, psi 0, that is psi at xl is 0, and psi xl plus h, that is psi 1, which is 0.001, small initial value to start the game. Okay, and k is e minus vx, already discussed in the theory part, and I have to integrate for I equals to range 1 to n minus 1 psi I plus 1, and whole thing is basically our Numerov integrator, which I this thing is converted into Python in a simple way, very simple thing, and it will, after doing this loop, it will return the psi, whole psi. Now we define a helper function, that is psi at L, that is not, that means other boundary, that is xr, that is right side of the wall, which is dead wall, artificial dead wall, which returns the value of the wave function at the right boundary for a given energy. This function help us to assess how well a particular energy satisfied a boundary condition. Psi at L E, that means for a given energy it will return the Numerov, it called the Numerov function, and square bracket minus 1, that means the last value of the psi, that means you integrate from one end to other end, and what is the value of psi, value particular at xl, last value of the wave function. To visualize how the wave function behaves at the boundary as a function of energy, if you change the energy, what is the value of psi at other boundary, that is xr right side, over a range of, say, a range of energy 0 to 10. So we create a empty array E, small e, and E range, that is np dot range 0 to 10, say at the step of 0.001. Now E in E range, E dot append, that means it calls psi at L, this function, this in turn call this Numerov function, that will be an array of points where for different energy values, what will the end value of the wave function will be stored in this E list. And if you plot this for a different energy range, the value of E, that means end point of the psi for a different energy levels, and if you plot this in a plot this using this code, you will get that uh, thing for a harmonic oscillator. That means you this is the energy scan for a different value of energy, where the psi function 0 will be a 0 value, that is clearly visible. It is easy to find out later on in which energy range you will get the eigenvalue 0. That means, sorry, psi value is 0. That means here the value, energy value is 1, near about 1, the psi at L is 0, near about 3, the psi is 3, psi at other end is 0, and near about 5, and etc. That means we get a clear idea of a given problem at the value of at what value of energy psi at the right boundary vanishes. So this help us to this is your ground state energy, this is your first excited state energy, this is your third, and etc. Use the bisect method from psi p dot optimize to find out the energy eigenvalue that makes the wave function vanish at the other boundary. In this case it is visible, that is one, that means you use bisect for two values we need for to find out the root, that means 0 to 2. Say eigen, this is eigenvalue, bisect psi at L, it calls psi at L this function, and you search between 0 to 2. The bracket, this bracket is based on the visualization, and you print that, and you will get the ground state energy is 0.99999 something, but analytical result is 1 for a harmonic oscillator in a reduced form. In actual form is half, and you have to multiply it by 0.5, but that is, it is actually in numerical its value is 1. And now we have to need the wave function. We already get the ground state wave function, ground state energy, and if you do say 1 to 4, and if you run this thing, this that the second energy level is 2.99, almost 3, and all that, and you can here you easily, if you 0 to 2, that you will get the ground state energy, and if you change 0 to 1 to 4, rather sorry 1.5 to 4, then you will get the second energy, etc. Finally using that given energy, I call the psi. Psi means Numerov, this thing will return the psi, the complete wave function, Numerov eigen with the eigenvalue, and we need to normalize it. Normalization means some a mod square integration from minus infinity to plus infinity mod psi square dx equals to 1. So a, the value of a is 1 by mod psi square dx from minus infinity to plus infinity, but here we integrate within our dead well, dead well wall, that means minus L to plus L over x. So I call trapezoidal function for integration psi square mod psi square rather, and you divide the psi by the norm, that means the value of this normalization constant, and you will get the actual psi. If you plot psi x versus psi, and you will get this thing, this is the ground state, that is Gaussian function. It is clear from the graph, this is the Gaussian function for harmonic oscillator. And if you want to calculate the first excited state, say 1 point, which is within which is near about 3, so that means the root finding should be say 3.2, and if you run this, the eigenvalue is 2.99, and if you run this part of the code, sorry, this is your you ignore this title, and this is your first excited state, that is odd state, and in this way you can find out n number of eigenfunctions and eigenenergies, and whole code is written here in a for understanding, and this is your the whole code, whole code is written here in a single block. And now if you want to study the harmonic rather than 1D box, infinite box, I make it L equals to 1, and you multiplied this by 0, then the potential will be a 0, that means potential is not a harmonic oscillator, say 0 into x, this is your 1D box, and you have to change the energy level here, same code but written in a contiguous manner, and the energy levels, first energy levels I have already told you, that is 2.46, and 2.46, that means here I run this, that means 2.46 here, that is 2 between 2 and 4, and we change this for root bisection, yes, from 0 to 4, 0 to just you check this graph, say 0 to 3 or 4, whatever you put that thing, 3, and you again run same code, yeah, This is the value, this is the ground state energy, which is 2.4670, which is basically your analytical result, same value, almost same value, and this is your ground state energy. This is your ground state energy. The second value is around 10, 9 point something, 9.8, the first excited state. And if you change that thing here, if you change that thing here, you have to scan little bit more, say up to 12. You have to change the energy range up to 12, and I can increase the accuracy a little bit higher, and and bisect is say 4 to 11. I hope you will get the second excited, first excited state. Yeah, this is your another cutting point, that is around 10, 9 point something, and if you scan that, this is your normalized first excited state, not a ground state. I have not changed the title. This is not a ground state, this is the first excited 9.86, which matches our analytical results. In this way you can solve any potential. First you scan this thing at psi at the other end, and then you try to find out the root, that means eigenvalue. And if you have any questions, you can write in the description box, and if you like, then you share and comment in the comment box. Thank you for watching. Thank you.